Okay, let's do the real hardware experiment in my office. You see in the back this hardware still running without a blower, so it's rather this time not noisy. If I switch it on, then it will be very noisy, so I explain some things without blower. Okay, let's turn around. Here you see the hardware. This picture fits exactly to the picture of the workbook. Here in the top, this is the desired value. I can switch desired value from 3.5 with this switch to 4.5. That is the 2-point desired value switching I want to demonstrate. Here you read the actual value of the temperature in volt, and in this instrument the real temperature is measured. You see here the temperature sensor over the blower, and the blower has a heater. Here inside you can see the heating wires, and here the sensor is just located directly in the blowing out position. Okay, furthermore you see 23.6 degrees centigrade are converted into 2.27 volt. You see there is a small error. I expect 2.36 volt. Then we have exactly a factor of 10. But that is just a cool demonstration that the controller only gets this value and has no idea what the real temperature behind is. So the sensor is responsible for accuracy. Here you see the PID controller with a capacitor. Two capacitors are switched in parallel and a resistor behind it. This is the R1, the 100 kilo ohm, and this here is the RC for the PDT1 part. Here is this switch can switch behind analog control and digital control. I switched just to analog control, and here you see some connectors. These connectors have two digital to analog output values, the blue and this yellow one, and here the green and this yellow one are analog to digital input connections to my ADC. This is a ground cable. I can measure desired and actual value, and also I can set the controller output, and I can set the desired value to this circuit. Let's have a quick look behind the box. Here you see the both digital voltmeters, just standard parts. Then here some plugs, and the electronic circuit is presented here. This is the actuator. You see this cooling for the 2 kilowatt triac circuit. Here our self-built operational amplifier circuit with the connections to the plugs to connect to realize the 4 operational amplifiers, and here finally 2 DC power supplies for my 2 for my digital voltmeters and 1 for the circuit. And finally, for later use, you see here a connection. If you have worked with this, you will really very easily detect that it's a Raspberry Pi 3, Model 3. Here you see the 2 ADC cards and 1 DAC card with I2C connection, and here some operational amplifier level shifter with the reason that this Raspberry can then give control and take over control instead of the analog controller. yeah, and make some other nice things. I will, maybe if this works, I will present it in this video. So let's stop here and start the next point. Yeah, now it is very noisy. You hear the blower working. I start with steady state situation at 35 degrees. Yeah, the desired value is 3.5 volt. The measured temperature voltage is also 3.5 volts. So we have now equilibrium point. Note there is a lamp. This lamp is an indicator for the actuator, just in parallel to the heater. So with this way to light, you have a good measure of the actuator working. So now I show you the step response of a step from 35 volt to 45 volt. I switch this circuit and then you see the light goes up, the temperature is increasing, then you have a small overshoot, then the temperature goes down, and after some seconds you have the final value 4.51. Now there is a small oscillation on it. This comes from the fact that the PID controller is not optimized. I have realized the PID controller with step steps 2 as described in the workbook and described in several videos, and now we have found the equilibrium point. You see there is a small change around 4.51 and 4.50, so the control error is really small. Okay, I will now connect this device to my computer, and then we will see some curves, because here you see some digital values but not a real curve. That's the next point. Now I have opened the program to control this temperature control system via laptop. This can be done with my WinDFC Sharp tool. There is an ADC card via I2C interface. So this is activated, and you see still that this is the voltage of the actual temperature. This is the voltage of the desired temperature. This then is the output for the actuator. So you see, if I slowly say 1 volt, this measured temperature now is increasing, because now I have 170 watt at my heater, and this increase this temperature. If this go down to 0, then you see the temperature goes down. This is a way to show you the measurement of the step response. So I close this box and open a real-time box. At this time you see only a small part of this. First I increase this sampling time to 100, and I increase the points to say 200, and I can now measure the unit step response of my process. In my workbook I have set the amplitude to 4 volt. I start with 0 volt, and if I click on run, then you can see this is the actual measured temperature. Now the system samples with 100 milliseconds, and if I click on start a process step response, then automatically this voltage is set to the actuator, and then we can see the 200 points. I think let's go to 500 points, 5 seconds for the process step response. Wait for this. I click on it. Now the lamp is burning, is lightning, and you see there is an increase of the voltage to temperatures here like 52 volts, 54, 55 volts, and after 5 seconds, 500 steps are 100 milliseconds of 5 seconds, you will see 50 seconds, sorry, 50 seconds, you will see the response. Yeah, the time scale goes to 50 seconds. Here you see we are reaching really a final value. So this could be used for identifying now the process model. Wait for this. Now the system goes out, and here you see the curve. The curve with fine grid, starting point, and here you see finally ending point at 5.7 volts. I see this is the step response with an offset, and the amplitude is not for the unit step response, because my amplitude is 4.5 volt. I want to have a unit step response. I repeat now the measurement by clicking this checkbox, and then automatically all values in the vertical axis are divided by 4.5 volt, and automatically the curve is cleaned from the offset shift. So I click again on run. This is the starting point. I think it's a good starting point. And again I can stop after 50 seconds. I repeat now the start, and you see now the temperature is increasing. The curve is displayed after 50 seconds if the measurement is completed. So we have to wait now for the curve. Here you see the number of points which are executed. So we have to wait 15 seconds, and then after this time you will see the new curve. It looks similar to this curve, but then this is a unit step response. So you see, this is the curve. We delete the last curves, delete all curves, and repeat the last measurement. This is now the unit step response. And you see the final value is nearly to 0.7, but this value set I also got in my workbook. Now I leave this window and go to the identification box. The identification box carries many identification methods. I try to use this by time function least square. Here you can now read this data. I make the box a little bit smaller, so, and I can stop the blower. Okay, that's rather good, because for the identification I don't need the blower. So I now have measured the unit step response and start identification. First I select the model in this identification method, which is described in Control System 2, chapter 8. Uses the step response data. I first make some init value method, then I click on optimize, and you see now after some seconds you see this curve with a delay. I don't want to have a delay in my model, so manually I set the delay to 0 and go back to optimization without delay. And here you see also a good fit, and the K is 0.72. I have calculated with 0.73. T1 is 8.1 second, and T2 is really exactly 1 second. So I think you see the identification gives a very good model to this situation. Note that I have measured the temperature curve from actuator value 0 to actuator value 4.5. If I want to have a better model fitting to my working points from 35 degree to 45 degree, that is what I want to measure, then of course I can repeat this measurement. In a linear system the values don't change, but in a nonlinear situation we will see different values. So I do the following: I make a new measurement. So this curve should be stored as screenshot. I think that could be good. And I start the new measurement with some new settings. I just want to save time for you, so I make the settings without video recording. Okay, now I run the controller with a constant offset of the actuator and add, after clicking on this button, add nearly 1 volt. That is exactly that what I want to see. But these points are very near to my working points in the control process. So I think I click on Start PSR. Here you see nearly 35 volt. If I click on this button, you see this is switched to nearly 0.95 volt larger. And now I wait just 50 seconds to see the new curve. This is offset cleaned and converted into the unit step response. Unit step response of the process. Process unit step response. So I shift up. You can see we have to wait now more than 13 seconds, 10 seconds, and then we will see the curve. Okay. I switch blower off. Here you see there is a little bit more noise, but that doesn't matter. The identification method ignores this noise or filters this noise away. So I leave this program and go back to my identification program, get the curve and optimize the curve. And you see the time constants unchanged, but the K is different. Here we have between these points we have a much larger process K from 0.7 to nearly 1. So this is nearly 0.3 times larger compared with 0.7. This is nearly 40%. So the controller gain must be decreased by 40%. Then we get a better control procedure. Okay, I'll show you the measurement of the reference step response using the analog controller, using the analog switch between 3.5 to 4.5. Yeah, so I think we should look for 20 seconds. I click on run. Now I have to switch on the blower. It will be noisy, and I click on this button that the measurement starts, but at the same time I will switch the button at my hardware. Before I start measurement, I wait for the zero initial conditions. That means this value, the starting value, should be constant. So I stop the video and wait for zero initial conditions. That means here we want to have constant values, and then I start measurement. Now measurement starts. Here you see nearly constant temperature, and now I switch by hand and click with my mouse at the same time. Time is running, and you will see just after 20 seconds my curve. Okay, that's not good. Now I repeat measurement. I go down with my switch to 35 degrees and wait for 0 initial conditions, and then start again by clicking on this button. I'm not sure why this starts 8 seconds too late. And now you see the reference step response with my analog controller starting at 3.5, ending at 4.5. You see there is an offset in my ADC, and there is an oscillation which is not really that what we have designed. So what I want to do and show you finally a digital PID controller with anti-wind up, so that you can see also in a good digital design you can have a much better behavior. Okay, now I have switched my hardware to the digital controller. I select a PID, I have designed it with methods described in Control System 2, running with 100 millisecond sampling time, still running to hold the 3.5 volt desired value. Now with this click the computer starts to control this value to 4.5 volt. You see very quickly this 4.5 volt is reached, and you see a rather constant value. After 20 seconds you will see a new red curve with my better behavior. You see very quickly you reach the final value, and then without overshoot and anything else you stay exactly at 4.5 volt. This is possible with a well-designed PID controller with digital mechanisms and a better identification. So I think this is enough for my demonstration. So I switch off the noisy ventilator. I hope you have heard anything if the ventilator is running. Here you see finally my temperature control system can be executed and run with a digital controller much better than an analog controller, or in other words, the analog controller has to be redesigned to much better values. Then of course I get also similar behavior, but of course the anti-wind up function is not available in analog hardware. Then we have only the possibility to work with a standard PID controller without anti-wind up. And the last thing what I want to show you is the curve just without waiting for a result, just a third curve with a PID T1 controller with better parameters K and T, but without anti-wind up, and then we check if this is also a good result. Yeah, the green curve is now the PID with the better values, but now with anti-wind up effect, which cannot be avoided in an analog situation. With digital controller and anti-wind up function are 2 lines or 3 lines in C. So I think this shows that a digital PID could be much better than an analog PID, in spite of the fact that we have some disadvantages, but these all things are discussed in Control System 2 in chapter 6. Okay, so far this experiment.